Everyone. So this video is going to be a solution walkthrough of a Math for Econ exam. What I'll do here is I'll show the questions in case you want to remind yourself of them, or if you haven't taken the exam and you would like to, and then I'll go over the solutions. So there is a collection, something like 8 multiple choice questions of this variety here. Then there's about as many kind of free response short answer. Oh, there's a collection of true and false. There's actually kind of a lot of those. And then there's some free response short answer mathematical essay. As you're seeing, the exam covers basically like pre-calc stuff, foundations, then some economic growth like compound interest, continuous growth, monthly growth type problems. There's some graph questions. I don't have the graphs in this version here, sorry. So that's a little bit useless. They're in the solution. Solving system of equations. And then we get up to single variable calculus, derivatives, and finding critical points, max, min, and so on and so forth, checking the first order condition and second order condition. This one right here, don't bother with that one. I struck that from the exam, and so I don't have the solution prepared here. Derivative, profit maximization problem. This one right here is thinking about distilling down this information into a demand curve, and then a cost curve, and then a profit maximization problem resulting from that effort. Here's the last one, so that's not going to be useful. All right, so let me put this away, and now here is going to be the solution walkthrough. All right, so the first one. Suppose the individual demand curve for the firm is given by Q is equal to 1200 minus 6p. Total cost function is C of Q is equal to Q squared minus 200Q plus 2500. We want to know what level of quantity maximizes profit. I want to write profit as a function of quantity and take a derivative and then set that equal to 0. That'll be my first order condition for a maximum, which will give me the profit maximizing quantity. In order to do that, I'll have to rewrite demand, which is Q as a function of P, as inverse demand, which is going to be P as a function of Q. So to do that, I'll move 6P to the other side, divide through by 6. That'll give me 200 minus 16Q. If I that's price, right? So if I multiply that by quantity, this right here is revenue. This is price, demand curve, substituted P in terms of Q, right? So this is demand curve times Q. This gives me revenue. And then minus Q squared plus 200Q minus 2500. That's the cost curve. And so this right here is my expression for profits. Notice I did this without parentheses, so we have to pay attention to signs. I'm subtracting costs, so it's going to be minus Q squared plus 200Q minus 2500. So that's what that's doing. Then I'm going to distribute this Q here. I could collect like terms and then take a derivative, or I could take the derivative and then collect like terms. What did I do here? I think I don't know. I collected like terms first. So this is going to be 200 plus 200 is 400Q. This is minus 16Q plus Q squared. I could think of, let's see, what did I do? Not plus Q squared, minus Q squared. So you could think of this is like a minus 1. You could think of this as like a minus 6/6. So minus 1 minus 6 is minus 7. That's why I wrote this as minus 7/6. Then I can take the derivative real easy. 2 times 7 is 14 divided by 6. That's this right here. The derivative of this is just going to be the coefficient, just 400. And then just setting this, or solving this for Q, I get a quantity of 171.43, which was not amongst our choices. So none of these are exactly correct. F. What's the average rate of change of this function? Y is equal to 5x squared minus 3x plus 7. The average rate of change, that's f of b minus f of a over b minus a. That's just our slope formula. So y2 minus y1 over x2 minus x1 equals m. It's like slope formula that gives us average rate of change. So that's all we're doing. So I'm going to evaluate the function at 3, and then I'm going to subtract off the function evaluated at minus 2. Then I'm going to divide by 3 minus 2. All right, so 5 times 3 squared is that's 45. Minus 3 times 3, that's another 3 squared, that's minus 9, plus 7. Minus 5 times 2 squared, so that's minus 20. And then minus 3 times minus 2 is going to be plus 6, plus 7. 7's cancel off. We've got to deal with some of the other things here. We get 43 minus 33. which is 10 divided by 5, excuse me, is 2, and that's the answer. Okay. So which of the following relationships cannot be characterized as a function? The answer here is E, mapping of each person to the languages they speak, because one person could speak multiple languages. Many people do, actually. Right. So which of the following represents the expression for difference quotient for the following function? So the function is 3x squared minus 7x plus 4. Difference quotient is going to be f of x plus delta x minus f of x divided by delta x, right? So we're just like adding a small amount. And then we take the limit to get the derivative as delta x goes to 0. It becomes an infinitesimal change. Anyway, so what's the difference quotient, though? I'm going to evaluate the function at this value. So this is going to be 3 times the quantity x plus delta x squared minus 7 times the quantity x plus delta x plus 7, then minus the function. You could distribute, kind of expand this, and then subtract off. Basically what happens is things with delta x's survive our cancellation. So that gives me 6x times delta x plus 3 delta x squared minus 7 delta x divided by delta x. So I'm going to factor out a delta x and cancel, and I'm left with 6x plus 3 delta x minus 7, so B. Question 5. Which of the following differential, or which of the following, what is the value, I don't know where I get that. What is the value of the differential which estimates the change in the function? So the function is y is equal to 1/4 x squared minus 3x plus 5. The differential is going to be dy times f prime of x times dx. So here's a small change in x times the derivative evaluated at x equals our estimated change in y. All right, so what's the derivative of this? 2 times 1/4 is going to be 1/2 x minus 3. Okay, let's evaluate that at our starting point, our initial, that's 10. So 1/2 times 10, 5 minus 3, okay, that's 2, times our small change in x. Oh, it's a big change in x. From 10 to 14 is 4. So that's going to give me, it's going to give me 8. Sure enough, if you actually evaluated the function and then saw the change, it'd be a bigger change than 8. But anyway, so the value of the differential was 8, B. Okay, suppose you can log in an annual interest rate of 6% that's applied monthly. You invest $5,000. How much should the investment balance be after 15 years? Collection of useful calculations. We're going to use our monthly growth formula. So that's going to be xn equals x naught times the quantity 1 plus rn, r over n to the nt. This x naught, that's what I'm starting with. That's my 5,000. Xn, that's what we're trying to find. That's what we're solving for. And then r, well, that's going to be my interest rate. This is applied monthly, so I'm dividing by 12. And then I've got 12 times 15. So monthly times 15 years. I should have written this as 0.06. So I was a little bit careless there. And also, I missed my 0. But what's going to happen is this is 0.06 divided by 12 is going to be 1.005 to the 180. And so that's this one right here, right? So in any case, we're going to be multiplying 2.454 by 5,000. And that's 12,270. What's the slope of the line tangent to the function? So what I want to do is find the derivative, then evaluate it at x equals 9. Okay, so the derivative here is going to be 3x squared minus 1/2 times minus 5, x to the minus 1/2, evaluated at x equals 9. 3 times 9 squared is 3 times 81, minus 2.5 times 1 over the square root of 9. So that's going to be 1 over 3. You get 3 times 81, and then minus 5 over 6. Okay, and that's going to give us 242.16, which is none of these. And so none of those are actually correct. All right, which of the following is algebraically equivalent to this expression? We've got to apply like a lot of our log and exponential rules here. First thing I've done is I just rewrote it. Second thing I did is I said, okay, well, natural log of x to the 1/3, I can write that as 1/3 times the natural log of x, right? That's going to get multiplied by a 3, which is going to go away. So it's just going to be e to the natural log of x. This minus 5 ln z is just going to hang out for a while. All right, so I can think of this as e to the natural log of x plus minus 5 times the natural log of z. And we know if we multiply exponent, or if you multiply things that have the same base, we add their exponents, which means I can pull these apart. And so I can write this as e to the natural log of x times e to the minus, or plus minus, 5 times the natural log of z. I just kind of skipped that step and wrote just x right there because it's e to the natural log of x. Their inverse functions. It's just going to undo each other and leave me with an x. And now this is times e to the minus 5 natural log of z. Oh, but I can use that rule I just did a second ago, and I could write this as z to the minus 5. So now I've got e to the natural log of z to the minus 5. These are it's the same inverse function. It undoes itself. And so I am left with x times z to the minus 5. But that's x over z to the 5th. And so, so that's this right here, e. Okay, so which of the following, of the following, which are true and false? So let's see. The second derivative, if the second derivative of a function is negative at a critical point, then the function must have a minimum there. So let's see. Second derivative is negative at a critical point. Function must have a minimum there. Well, for a minimum, we want the function to be opening up, right? So second derivative is going to be positive. In a supply and demand model, endogenous variables respond to exogenous shocks, but not the other way around. Yeah, that's right. So our endogenous variables are like price and quantity. Our exogenous shocks are like prices of related goods, changes in income, stuff like that. So those things affect the equilibrium price and quantity. The price and quantity doesn't affect the other things. If a function has a local max at a point, its derivative must be 0 at that point. Now, we could have like a punch function where you have like a hole it's missing, or that could be the maximum, or you could have like a corner or something like that. So you can have a lot of different things or discontinuous jump. Well, however our interval is. Anyway, so you can have a max, but maybe the derivative's undefined. If a function is monotone increasing, it must be differentiable everywhere. No, because so monotone increasing, we have this increasing function. I mean, maybe like our step function or something is non-differentiable, but it's still like still increasing, monotone increasing. If a function has a discontinuity at a point, it cannot have a local maximum or a minimum at that point. That's false for the same reason as I said up there. So you can have a discontinuity, and that can be a local max. It's just not going to have a derivative, and certainly not derivative equal to 0 at that point. A function can have an inflection point without having a local max or local min. Sure, yeah. So it can, you get things changing directions, and then you don't have a max or a min. So a good example of that is like, if you take the function that's going through the origin, you have the so like x to the 4th or something, and then the first derivative is going to be 0 at the origin, but then the second, you look at the second derivative test, and it's going to tell us it's an inflection point. Second derivative is always positive. Function's concave down everywhere. Let's look at the function x squared. First derivative is 2x. Second derivative is 2. That's always positive, but the function's concave up, right? So, convex. All right, so below our graphs, identify the statement for the graphed range of the function. The second derivative is never negative, is either true or false for the function. No explanation is necessary. It's a little bit hard to see here, sorry. This is like x squared. Let's see, the second derivative is never negative. That's true, we just said the second derivative is gonna be 2. Right here, second derivative is gonna be minus 2. So it's actually always negative. For this one, the second derivative, let's see, it'll be 3x squared. It could be 6x. So that second derivative for negative values of x will be negative. And then the sine function, let's see, you have to think about the derivative if you want to do it that way. Or you could just do it, so you kind of just look at the graph, and you know that it's gonna be false. And then let's see, second derivative is always negative. Well, the derivative of the exponential function is just the exponential function itself, which is just always going to be positive. So that one's true. All right, so short answer, you deposit $15,000 in an investment account, grows continuously. So we're using our exponential formula, at expected rate of 4.5% per year. How long is it going to take to reach $250,000? So you need the formula. There should be no plus or minus signs, though you can use fractions. Don't do the calculation. So our formula is going to be 15,000 times e to the 0.045t equals 250,000. So I skipped a step when I wrote this immediately. Take the natural logs of both sides and then divide through by, well, you could divide through by 0.045. So actually, not only did I skip a step right here, I also didn't write the answer. So the next thing that we wanted was t is equal to natural log of this stuff divided by 0.045. We want to divide through and solve this for t. Because what do we want to do? Put the formula, estimate the number of years. Yeah, that's right. So we want to go at least that far. Solve the following system of equations for x, y, and z. It's going to be 1, 4, and then minus 2. So I took the first one, x, and I solved this for x, 5 minus y. Then I looked at the second one. I solved this for z. Z is equal to 2x minus 4. So then what I did is I went to the last one and I replaced z with 2x minus 4. So I've got 3y plus 2x minus 4 equals 10. Collected like terms, basically moved that 4 to the other side. And then I substituted again for this x, and I wrote this as 3y plus what was sitting here. This is a 2x. Yeah, this is the 2x from up there. 2, I was worried if it was a z, times 5 minus y. And then distributing, we got 3y plus 10 minus 2y is equal to 14. Collecting like terms, I'm going to get, let's see, on this side, I'm going to get 14 minus 10 is 4. And then on this side, I'm going to get 3y minus 2y is 1y. So that's y equals 4. With y equals 4, then I get x, 5 minus 4. Okay. And then with that, I can get z. So 2 times 1 minus 4 is going to be minus 2. 2 minus 4 is minus 2. Okay, identify which of the following, identify all x values that are part of critical points of this function. And then identify if they're max, min, or neither. Okay, so my derivative here is going to be 3x squared minus 12x plus 9. Okay, I've got to factor out this 3, and then I've got x squared minus 4x plus 3. And I want to factor this thing because the zeros, the values that make this statement true, make this equal to 0, are going to be my critical points. So this is the zero product property. That's what lets me set this equal to 0. So if this is 0 or this is 0 or both at the same time, then the whole thing is 0. Zero product property. Okay, 3 times, which allows me to write this as x minus 1 equals 0 or x minus 3 equals 0, which is how I solve for x equals 1 and x equals 3. Although maybe what you remember is just like, if you look at this, the value is just going to be 1, the value here is going to be 3. Okay, fine. So we've got our critical points. Now what we want to do is look at our second derivative and evaluate if we have, evaluate the signs. We know if we have a max or a min. Second derivative here is going to be 6x minus 12, right? My inflection point is 2. Okay, fine. So, but what we wanted to do is evaluate my second derivative at x equals 1. Okay, so it's going to be 6 minus 12 is minus 6. And then, let's see, 6 times 3 is 18 minus 12 is positive 6. So we have a maximum here because second derivative was negative, so it's opening down. So we have a maximum. And then we have a positive here, so it tells us we have a minimum at x equals 3. 14 we skipped. What's the derivative here? Full credit requires the answer to have only 3 additively separate terms. Okay, so I'm going to take the derivative. It's going to be 2 times the quantity x to the minus 2 plus 3x to the 5th. Then I got to take the derivative of the inside. I reduce this power by 1. That's just hiding there. It's like a 1 right here. I didn't bother to write. Derivative of this is going to be minus 2x to the minus 3 plus 15x to the 4. Okay, now I've got to distribute, well, FOIL And so I'm going to get x to the minus 2 times minus 2 to the times x to the minus 3, x to the minus 2 times 15x to the fourth, 3x to the fifth times minus 2x to the minus 3, and 3x to the fifth times 15x to the fourth. And then I'm going to multiply through this 2. Well, collect like terms and then multiply through the 2. Collecting like terms, I get minus 2x to the minus 5 plus 15x squared plus minus 6x squared plus 45x to the ninth. I collect like terms here, so that's going to give me, let's see, that gave me 15 minus 6 was 9x squared, but I've got this 2 here, so I get 2 times minus 2 is minus 4x to the minus 5. 2 times 9 gave me, because 15 minus 6 gave me 18x squared, and then 2 times 45 gave me my 90, x to the ninth. Okay, profit maximization problem. So you've created a new gourmet energy drink to set up outside the gym and sell it. Word spreads that it significantly boosts performance, demand soars. Price of $2 per bottle, you sell 600 bottles per day. For every 10-cent increase in price, you sell 5 fewer bottles. Fixed cost per day amount to 300. Each bottle costs you 80 cents to produce. Determine the price at which you should sell the energy drink to maximize profits. Okay, so at a price of $2, I'm going to sell 600 units. However, that amount falls by 5 for each additional 10 cents. So I'm going to write out my demand function. It's going to be this. X equals 600 minus 5 times the quantity, P minus $2 divided by 0.1. And the idea is if the price that I'm selling rises above $2, for every 10-cent increase in price, I'll sell 5 fewer bottles. And this will capture that. Let's see. So, this 5 was the 5 fewer bottles. Yep. And then I'm going to factor out, factor out the minus 10, which amounts to multiplying this right here by 10. That's why I got 50, right? And so then I've got x is equal to 600 minus 50 times that quantity price minus 2. Distributing, I get 600 minus 50p minus 100, minus 50 times minus 2 is positive 100. That's why I got 700. Okay, so that is correct. Now this is my demand. I'm going to drop this into the revenue portion, multiply that by P. That gives me revenue. And then minus cost. Here's my fixed cost. That was 300 times 80 cents was the marginal cost times the quantity written in terms of price was this 700 minus 50p bottles. Then it's a matter of just like multiplying through and expanding. So this is going to be 700p minus 50p squared. This right here is going to be minus the quantity 860, and then this is going to be, or where did that come from? This is 80% of 700 is 560. 80% of 50 is 40. That's where that's coming from. And then I'll get a minus an 860 is minus 860. Minus a minus 40p is a plus 40p. So I'm going to get 740p when I collect like terms there, minus 50p squared, and then minus 860. When I take the derivative, I'm going to get a minus 100p plus 740, and then obviously just solving for price, it's going to give me 740, which was the price I was looking for to maximize profits. You can check the second derivative. Take the second derivative, it's going to be minus 100, always negative. That tells us we got a maximum. Okay, lastly, below is a graph of the function, darker grid lines for the for the y-axis. Sketch the first and second derivatives. Okay, so here's the function. So below, let's see, so for negative values of x, first it's increasing. Then we have our, the original graph. Then we have our critical point. Then it's decreasing. We have our inflection point. We have our local minimum. And then it's increasing again. Okay, so I'm going to get zeros at minus 1 and at 1. Okay, so I have to have zeros at minus 1 and minus 1. And then I have this thing, let's see, it's positive, then it's negative, then it's positive. So sure enough, I've got it positive, then it's negative, then it's positive. This is my first derivative, right? So, you could think of this as something like, what's the function? It's something like a cubic function, like x cubed. And then my first derivative is like is a quadratic, so it's like 3x squared. Only not exactly, because that doesn't give me these zeros, right? And then I have to take the derivative of that thing. So if I was just, it's not the right function, but like just so we can visualize it. Suppose the function was x cubed. First derivative is 3x squared. Second derivative is 6x. So function is cubic. First derivative is quadratic. Second derivative is linear. You know. So let's see. This thing needs to be negative. It's decreasing. So the second derivative is going to be negative before 0, right? And then it's going to be increasing after 0. So it's positive, right? So second derivative is going to be negative below 0 because the function's decreasing, and then past x equals 0, the second derivative's got to be positive because the function's increasing. Okay. Anyway, so that's the exam. Hope you enjoyed the video. Hope you did well, and I'll see you next time.